Okay, so I will start this lecture. Actually, it is Seismology 4, but you had not yet Seismology 3, because Seismology 3 was supposed to be VED, and we switched to be coherent. So far you have seen a first lecture on body waves, the second one on normal modes, and now we present the third kind of seismic data, surface waves. Okay, so here is the outline of my presentation, and I would like to introduce you with seismic anisotropy and why it is at the same time complicated but at the same time very useful for gaining insight in geodynamic processes. And afterwards I will present surface waves. I will present you some seismograms, and I will show you only some scientific issue that might be useful to use seismic anisotropy. And if I hope I will have time to discuss the point which was addressed 2 times about attenuation and the fact that the quality factor is constant with frequency. And I will show you that one possibility might be due to scattering due to seismic anisotropy. Okay, so what I would like to convince you is that seismic anisotropy is not a second-order effect, but it is present at all scales. And I will show you that we have to try to understand the different processes from the micro scale up to the observation scale. And different mechanisms are in play, and I will detail the different mechanisms to align minerals and also to create seismic anisotropy. So I would like to say that the anisotropy is the rule, not the exception, and we really have to take account of anisotropy when we want to explain seismic data. Of course, what is quite difficult is that we have the observed anisotropy, and the phase of interpretation is more complex because we have non-unique interpretation in different range of the Earth. First, I would like to start with some confusion for students, which is a confusion between anisotropy and heterogeneities. And for example, you might have an homogeneous medium, such as composed of olivine, and this medium can be completely homogeneous, but will be anisotropy. On the other side, you can have very heterogeneous medium, where we have a very complex layering, and all the layer can be isotropic, and so it's different kind of medium, of course, and we will have to separate the heterogeneities of isotropic heterogeneities and heterogeneities of anisotropy. What makes, again, things complicated is that the Earth is at the same time heterogeneous, anisotropic, and anelastic. Okay, so if we consider now the seismic anisotropy at all scales, we can start with the microscopic scale, and of course you all know olivine, which is a very strongly anisotropic mineral, more than 20% of anisotropy, and we have to understand how, when you have a upper mantle composed of olivine, you will preserve the anisotropy at different scales. And so afterwards we have some aggregates, and the aggregates must be aligned to preserve large-scale anisotropy. But we have also some other effects which can be important. For example, you can have some fluid or crack distribution, and in that case you will also have some anisotropic effect. And I try to separate what I call intrinsic anisotropy, which means it is present at all scales, from the mineral scale up to the micro scale, and extrinsic anisotropy, which is due to mixing of different processes. And another extrinsic anisotropy is when you have a fine layering. In that case, the effective medium is also anisotropic. And finally, at very large scale, I only show the example of the PREM, which for the first time displayed anisotropy, one specific case of anisotropy. I will come back later on that. And For the PREM model, we have 3 anisotropic parameters in the top 220 kilometers. And of course, you see that we have these all processes in play. And what we measure is seismic waves, so with some seismic wavelengths. And seismic waves only see some apparent anisotropy, and they are myopic in the sense that from seismic waves, we have only access to long wavelengths, and it's very difficult to go back to the very small scale anisotropy. And so when we have some observed or apparent anisotropy, we have a mixing of these different effects, and a very challenging issue is can we find the percentage P of intrinsic and extrinsic anisotropy. Okay, so let me start by the different processes giving rise to anisotropy. Lattice preferred orientation. That's a very old figure, but which explains why seismic anisotropy can be very useful. You have here the olivine, and you have the different crystallographic axes, and you see that the fast axis is about 10 kilometers per second, which is large, compared to the slow axis, only 7.7 kilometers per second. So you see that the difference in velocities is about 20%. And an interesting observation made many years ago is that the fast axis tend to be aligned with the flow direction, which is sensitive to the strain, and it tends to align in this main direction of strain. And you can easily understand that, of course, if it is effectively observed at very large scale, it's very useful because we have a way to map convecting flow in the mantle. Of course, we have some other minerals, such as orthopyroxene, which have different tendency of orientation. It tends to decrease the amplitude of anisotropy, but still, if we combine both, we still have a percentage of anisotropy larger than 15%. Okay, so you can easily understand the interest in seismic anisotropy if we have this alignment of minerals in the Earth's mantle. Okay, so go back now to the different processes. And of course, olivine is very anisotropic, but anisotropy must be preserved at large scale, and we need some process. It is a lattice preferred orientation, and if we need also a coherent strain field. In that case, we have different grains. I'm not sure it is really realistic, but anyway, if you have all the fast axis of olivine aligned in a coherent way, the large-scale anisotropy will be different from 0 at larger scale. But if we have some incoherent strain field or a random orientation, the average anisotropy will be close to 0. Okay, but when we have this coherent strain field, the observed anisotropy will reflect an inner organization of the Earth, and so can be very useful in that respect. Now I would like to make very simple calculation. I would like to show you that seismic anisotropy is not a second-order effect by assuming that we have some perfect orientation of minerals. And so I took a very simple case, a convective cell with upwelling and downwelling. And also, of course, when you have upwelling, usually it is hot. When you have downwelling, it is cold, and you have horizontal flow. And I will try to estimate what is the effect of anisotropy on the amplitude of heterogeneities, and what is the effect of temperature, which will also give rise to heterogeneities. And we did very simple calculation for doing that. And here we have upwelling in red, downwelling in blue. And if you consider the difference between blue and red curve, you can estimate, because we assume that we have the same alignment of minerals, we can estimate delta T, which is the amplitude of heterogeneities due to temperature. And now if we consider the difference between vertical and horizontal flow, we can estimate the effect of alignment, the effect of anisotropy, and you see that if you have perfect alignment for a mixing of olivine and orthopyroxene, we have exactly the same amplitude. And so it is to demonstrate that we cannot neglect seismic anisotropy when we try to explain lateral heterogeneities in the Earth. Okay, but as I told you, we have other effects which can give rise to seismic anisotropy. If we have crack distribution, if we have fluid inclusions, if we have melt, and in that case, we can have also what is named shape preferred orientation. Usually, it is related to the stress field, and it is observed in different parts of the Earth. For example, it is observed in the crust, and when you have this kind of distribution, it is aligned by the stress field. So if you have a compressive stress, it tends to open the cracks of the fluid inclusions, and in the opposite direction, it tends to close the cracks and the fluid inclusion. We also propose that we have also this kind of fluid inclusion in the inner core, which might be a possible explanation of the strong seismic anisotropy in the inner core. Okay, so an extreme case of shape preferred orientation is the fine layering. As I show here the model by Hitoshi Kawakatsu, who proposed that to explain the large difference between VSV and VSH in the asthenosphere, he claimed that we have a layering, we have a millefeuille model. It is I don't know if you know this French pastry. It's very good, and you have a mixing between isotropic layers and pockets of melts, and the equivalent medium is a vertical transversely isotropic medium with a vertical symmetry axis. In that case, I will go back to that. You will need 5 parameters to explain this kind of apparent anisotropy. So during the last year, we tried to estimate this kind of effect of layering, and we went back to the old paper of Bacchus in '62, which was improved recently by the homogenization technique. And we showed that if you have, that's a simple example, when you have a periodic isotropic 2-layered medium, and in the top 200 kilometers, if you have a 10% of heterogeneities between 2 layers, you can calculate the equivalent effective medium. And what we find is that the equivalent anisotropy can be quite large. It can be up to, you see, for Xi, it is related to S-wave anisotropy. Anyway, I will go back to these different parameters later. And you see, you can have anisotropy up to 15%, so it's quite large. And an interesting.
Define the eta, phi, and.
I will do it later. Okay. Yeah, okay. It's only to illustrate the fact that we have different effects, and of course I will explain these different parameters later. Yeah, and the important point is that we can find L is related to VSV, N to VSH, and we can make the average of this medium, and we can show that we do different averaging, and so we get the amplitude of the different parameters. And by the way, it's a very simple way. We show that it might be also an alternative interpretation of what we observe in PREM, that we might have some layering in the lithosphere. And okay, but it's also not only due, the anisotropy of PREM is not necessarily due to lattice preferred orientation. But of course, I realize that I have to explain later the different parameters. So we have at least 3 different processes related to different physical phenomena. And the most popular, of course, is LPO, because it is very simple to interpret, but we must not forget that we have also other processes in play. And of course, different things can modify seismic anisotropy, of course, the mineralogy through LPO, but we have also water, fluid content. But the interesting point is that seismic anisotropy can be used for investigating present-day tectonic and geodynamic processes. Even if we consider frozen-in anisotropy, we can also investigate past processing. And another application I will not detail is that seismic anisotropy can be used to monitor the stress and the strain field in seismogenic zones or in volcanic zones. But the main issue is to separate these different kinds of anisotropy in different layers because, of course, you see that they correspond to different interpretation. And in addition, the Earth is layered, and we can have different kind of anisotropy in the different layers with different processes. Okay, so what we do from a practical point of view, and what I try to summarize here, is that mineral physicists work in their lab and they investigate the different minerals. They also try to understand the different processes which acts on the aggregates, isotropic or anisotropic aggregates. These minerals are modified by mantle convection. And finally, what we observe is different kinds of parameters. And again, I will detail this Xi parameter and G parameter. Xi is related to the difference between VSV and VSH, and G parameter is related to the azimuthal variation of S-wave velocity. Okay, again, I will go back to that. And of course, what we have to do is to do the downscaling. We have long wavelength observations, and we have to interpret this observation in terms of convection and even in the future in terms of mineralogical composition. Okay, so now to measure anisotropy, we need seismic data. And I only want to mention that what we use are basically broadband data, and we have the backbone of the Federation of Digital Seismic Networks. And as you can see, we have, during the last 30 years, more than 300 stations, so we have a good coverage almost everywhere in continents, except in Africa. And we have also some stations in islands. But of course, the coverage is far from perfect because we have no stations on the seafloor. And so in the future, we expect to improve the coverage of the whole Earth by installing ocean bottom observatories, or at least portable ocean bottom stations. Okay, so during the last 10 years, there was a great development of a regional network. And I like to show this figure. You know, for example, of course, we have the backbone by Global Seismic Network. There was a US array. And here we have the stations in Europe. And it's interesting to see the difference between the US and Europe. You see that in US you have a very regular spacing between stations. And in Europe it's more related to different national networks. So we still have some progress to do in Europe. In China you see that you have also a lot of broadband stations with a gradient from the coast up to the inner China. And the denser network is in Japan, where we have, of course it is not the same scale, and we have approximately 1,000 stations in the whole island with a spacing of about 20 kilometers. And what we do during the last decades is also to install some ocean bottom stations. And I show here the example of a French experiment, a French-German experiment in the Indian Ocean to investigate La Réunion hotspot. So we have a lot of data, and three-component data in a large frequency range between 20 Hertz to 1 millihertz or 0.1 millihertz. And so we have to process this data to get information on lateral heterogeneities and anisotropy. Okay, so what kind of data can be used for investigating seismic anisotropy? Of course, we can use body waves, and we can use surface waves. And the most popular way to investigate seismic anisotropy is to look at the shear wave splitting. Shear wave splitting means that when you have an incoming S waves, when it comes inside an anisotropic medium. It's split into two waves. And since the medium is anisotropy, these two waves with different polarization will propagate at different velocities. And finally, you will have a delay time between the two waves, and which can be used for getting information in the anisotropic medium. But this issue will be addressed, I guess, by Maureen Long next week. I will more focus on the surface waves. And for many years, people realized that we cannot explain Rayleigh and Love waves by isotropic medium. And so in the 60s, it was necessary to introduce what was named, it's not exactly a good name, the polarization anisotropy. And later on, in the 70s, people start to investigate the azimuthal variation of the phase or group velocities. The effect on amplitude are also present, but much more difficult to investigate, so I will not show example on that. Okay, SKS splitting. As I told you, it's a very popular way because it's very unambiguous. When you have S wave arriving, it converts in the outer core in P wave, and if you have isotropic medium, you will have only SV wave, but if you have some anisotropy, you will observe as well SH wave. And that's a very old observation by L.A.B, where you see the two components, transverse and radial component, and you see that they have a phase delay, which can be seen here, and so you can derive from these measurements delta t and also the azimuth of the waves. And it was investigating largely by many people, and okay, again, Maureen Long will do that. And I show here one compilation. It's not the most recent one. I guess Thorsten has probably a more recent one. But I show that because most shear wave splitting measurements have been made in continents, and some of them very, very few in islands. But you see that most of the Earth is completely unknown by shear wave splitting. And so that's the reason why we need surface waves. And it is the only way to investigate the structure below oceans.
What do those symbols mean in that plot?
Sorry?
Could you tell us what those symbols mean?
Which symbols?
The red line.
Ah, okay, yeah. It is the orientation of the fast axis okay, I forgot. Yeah, you are right. Good point. Yeah, of course, as I told you, from SKS splitting, we have access to the fast axis, and it is what is plotted here. And so geologists are doing, with one measurement, geologists can reconstruct all mountains and so on. And so by using this
another question. So since the Earth is rotating at a reasonably fast speed, it's distorted into an ellipse, right? It has ellipticity in different layers. So it has a preferred orientation also. So
no, well, you know, it's not the same time scale.
I mean, my question is, would that preferred orientation of Earth's rotational axis have an isotropic effect?
Okay, I don't think so, but I have to see. I guess the rotation is very slow process compared to the propagation of waves. No, so I don't. Yeah. Yeah, but I don't know if it can affect the orientation of minerals.
There was a paper published recently about I guess SCS bouncing waves, and just like Foucault's pendulum, right, moves as the Earth moves around underneath it. So a wave that reflects off of the core mental boundary, for example, will be slightly shifted by a degree or two when it comes back. It's called some kind of oscillator. I forgot the name. But there was a paper recently about it.
Okay, so Thorsten?
Also, as Bruce pointed out, which is sort of a little bit esoteric, but the spin of the Earth changes the instability and the kinds of wavelengths of convection. So if you're at a very low Rayleigh number, as you might be when the inner core freezes, so just before it shuts down, it might freeze in a different sort of convective pattern as when the Earth wouldn't be spinning, and so
Okay. Yeah, for the inner core, of course, the orientation of minerals is also due to the rotation of the inner core.
The elasticity of different layer depends on the density inside that layer. So like the elasticity of the core is probably less than the elasticity of the Earth's surface. So elasticity of Earth's surface is 1/300 or 1/298. But the elasticity of the core is probably 1/600 because it's twice as dense as the average density of the Earth, right? So you would expect there are slight deviation from a perfect sphere to different degree in different layer of the Earth. So I would assume that would have some effect.
Okay, maybe I don't. To be honest, I don't know, but it might be investigated, of course. Okay, so this figure shows that we have a shear wave splitting measurement, but we have no measurements below oceans, and so we have to look at surface waves. I show this example of seismogram from the book of Stein and Weiss session, and you have the three components: radial, transverse, vertical components. And you see that on the radial and the vertical component, we have the same kind of waves. And you can see that for teleseismic distance, I mean for distance more than 10,000 kilometers, surface waves here are the most energetic waves compared to body waves, which can be seen before with, you see SKS and SS and so on. So we have Rayleigh waves on the radial and vertical component, and we have L.A.B waves with the different velocities, which correspond to the transverse motion. And we can see even in this figure that we have a complexity in the wave, in the different frequencies, because you see, for example, this frequency is traveling faster than others at shorter period, and we have the same effect for L.A.B waves. And so we have to understand how can we explain these surface waves, which can be shown to be guided waves by the surface. And surface waves, I told you, are guided waves by the surface, whereas body waves are propagating inside the Earth. And you can easily understand that since they are guided by the surface, they are sensitive to the upper part of the Earth. And we will be able, by using surface waves, to investigate the structure below oceans. And from body wave, you have more, for teleseismic events, you have more deeper information. And I show here this kind of records, because vertical, radial, and you see the very large amplitude of surface waves compared to body waves here. Okay, so we need to understand what are surface waves. And surface waves, we have two kinds of surface waves. We have Rayleigh and L.A.B waves. And I guess it's good to have this talk now after body waves and normal modes, because all waves are satisfying the same elastodynamic equations, but with different boundary conditions. And Rayleigh waves are only related to the coupling between P and SV wave. And you see that there are a complex particle motion with an elliptical particle motion when they propagate. It's like when you are on a camel, you go forward and you go up and down. So it is a kind of particle motion of surface waves. L.A.B wave is different. It is guided SH waves. And you see that you have transverse particle motion when the wave is propagating. Okay, and of course, as I told you, Rayleigh waves are guided waves due to the coupling between P and SV wave, and at very long period. And if you consider waves making many turns around the Earth, you can retrieve from Rayleigh waves the spheroidal modes, and from L.A.B waves you can find the toroidal modes. So, same basic equations, but different boundary conditions and different kind of propagation. Another property of surface wave is that they are dispersive. It means that their velocity, and we can define either phase velocity or group velocity. Phase is related to one specific wave propagating, and you look at a specific wave with given frequency, and we can find the phase velocity. The group velocity is related to the propagation of energy. And as you can see, according to the period, you have different phase and group velocities. It is due to the dispersion properties of surface waves. And you can understand that when you consider very long period surface waves corresponding to very long wavelengths, you see, for example, at 200 seconds, you have about 4.5, so you have about a wavelength of 900 kilometers. You will be sensitive to deeper structure than if you consider short period surface waves at 40 or 50 seconds with a wavelength of about, at 50 seconds, about 200 kilometers, which is sensitive to the shallower structure. And so we use the phase or group velocity dispersion curve to retrieve, to invert for the structure of the upper mantle. Okay, let me show an example of seismogram and synthetic seismograms, because of course when we want to use surface waves, we need to make synthetic seismograms. And by the way, a very popular way to do it is to use a normal mode summation. I don't know, by using eigenfrequencies and eigenfunctions derived from normal mode theory. And you can see it's not so bad. We have some good agreement. We have some difference in time, but we have some the synthetic seismogram, which is calculated for a 1D Earth model, usually the PREM model, is not so far from the real seismogram. I also show here that we have different kind of modes for surface wave. We have the fundamental mode, which is the most energetic mode here. It is named n equal to 0, but we have also overtones and also named higher modes with different velocities but a smaller amplitude. As you can see here, it is normalized, but you see the relative amplitude. And fundamental mode usually is the most energetic mode, except when you have very deep earthquake, when you can have a good excitation of higher modes. And so that is the base of the use of surface waves. And we have different approaches to explain these surface waves. We can use only the phase information. It is what is usually done by classical techniques. In that case, we measure phase and group velocities, and we do the regionalization. So we try to locate for different parts of the Earth these local phase and group velocities, and afterwards we do the inversion at depth, and that is a classical technique. More recent technique is the waveform inversion. In that case, we invert for the whole waveform. So we, in a sense, we work in the time domain, but we can work as well in the frequency domain, and we do the inversion at depth directly. Okay, and so now we can wonder what is the effect of seismic anisotropy on surface waves. Okay, so as I told you, we have to design a complete anisotropic tomographic technique, and when we want to make tomography, we have to solve two problems. The forward problem, it means that we have to relate the data space to the parameter space, and I will define what is a data space. Basically, is the space of seismograms and seismic data. We have also to define what is named a covariance function of data, which is related to the errors on the data. And the parameter space, it is what we have to work on when we want to take account of anisotropy. And again, we have to define a covariance function of parameters, so it's not so, I will not detail. And usually we start with a reference Earth model, and for example, I showed you that we calculate synthetic seismogram by using the PREM model, and we use the difference between the synthetic data and the observed data to solve the inverse problem. And so the inverse problem, we have many different techniques, and I guess it will be addressed by Ved next week. We have to find the inverse operator, if you like, of the G, which relates data and parameters. Okay, so I will not detail this tomographic technique, but only focus on the parameter space. And I try to avoid equations, but that's the only slide with equations where we define what is the effect of anisotropy. And so seismic anisotropy is defined through an elastic tensor, and this elastic tensor you see has 4 indices. So it has 21 independent elastic moduli, which is a lot, of course. And I remind that in the isotropic case, we have only 2, lambda and mu. And if we want to see the effect of anisotropy on surface waves or normal modes, we have to calculate this complex tensorial product between the strain tensor, epsilon, the elastic tensor, perturbation, and we can relate by using minimization principle. We can relate this product to the variation in phase velocity. So it's a complex calculation, but it can be done from the analytical and numerical point of view. So, of course, we can apply the same technique for Rayleigh and Love waves, and what we find is that the phase velocity perturbation can be expanded as a function of the azimuth. The azimuth corresponds when you have an earthquake and a station. If you consider the path between both, the azimuth is the angle of the ray with respect to the north. And so we can show from a theoretical point of view that we have this expansion in a Fourier series with this term is named the 0 psi term. We have 2 psi and 4 psi. And that is a first order perturbation theory. And due to the fact that we have a fourth order tensor, which is complicated, the first order perturbation theory gives you rise to 2 psi and 4 psi terms. And I will show that what we have in these different alpha terms, which are the different azimuthal terms. And we have inside the sensitivity kernels, and we have also the parameters that we can retrieve. Okay, so for surface waves, we have to do a first transformation between a first order tensor into some kind of matrix, 6 by 6, but with the same number of independent parameters. And what we find is that for explaining the effect of anisotropy on surface waves, we have to we can see the effect of 13 parameters. And we have here the different azimuthal term. We have the constant term, which corresponds to the average over all azimuths. And here I define the different parameters I mentioned previously, A, C, F, L, N. So when you have an anisotropic perturbation, we see that we have these 5 parameters. So we move from 2 parameters for the isotropic case to 5 parameters for this 0 psi term, and 4 of them can be easily related to seismic waves. For example, A is related to VPH, C to VPV, L to VSV, and N to VSH.
How can you define SVSH?
Oh, it was not done by during the class of okay. When you consider a S wave is a transverse wave. So if you have a propagation in a given direction, you can define 2 orthogonal polarization. If you have a wave propagating this way, you have the vertical polarization, which is SV, and the polarization perpendicular to the ray propagation in the horizontal direction is named SH. Okay, so we have these 2 kinds of polarization for S wave, and we can, of course, they are sensitive to different elastic moduli, and it is what we will try to find. So this 0 psi term gives access to the equivalent transversely isotropic medium with vertical symmetry axis, and we need 5 parameters. So in the simplest case, of anisotropy, which is a classically named a VTI medium, we need 5 parameters. If now we want to see the azimuthal variation, I mean in the horizontal plane, we have to define additional parameters, and we have BCBS, GCGS, HCHS. And these parameters are related to the azimuthal variations of, for example, BCBS to the azimuthal variation of VPH, and GCGS, which is quite important, related to the variation of VSV. And we have also, as I told you, some azimuthal terms, and in that case, EC is related to the azimuthal variation of SH velocity. Okay, so you see it is, at the same time, it's quite complex because from a theoretical point of view, we have access to 13 parameters. We can wonder why not 21. Actually, not 21 because surface waves are propagating along the surface, so surface wave cannot see the difference if you propagate in one direction or in the opposite direction. So we miss by surface weight some elastic moduli. But even 13 parameters, it is a lot of parameters to retrieve compared to the isotropic case where we have only two parameters, VS and VP.
Can I ask a question?
Yes.
This assumes that you have horizontal anisotropy that's in horizontal planes with some variation in 3D. But what if you have vertical anisotropy?
For the vertical anisotropy, in that case, you have no azimuthal variation. It is a case where you have a transversely isotropic medium with vertical symmetry axis.
So if you have anisotropy that actually isn't a vertical direction?
Yes. Yeah, you need only 5 parameters.
Okay. But what if it's dipping? What if you have something that's neither horizontal or vertical and actually flow?
Oh, you know, when we do this calculation, we do not make any assumption, except we have small, so it is very general parameters. And of course, it can include the case when you have only a tilted anisotropy. Yeah, because when it is a vertical anisotropy, you have no azimuthal variation. Okay. But when you tilt your symmetry axis, of course, you have an horizontal projection, so you have azimuthal variation. And in that case, you have to take care of these azimuthal terms.
But is there an ambiguity between the amplitude of that azimuthal anisotropy and whether it's dipping or not? So so you're going to measure a certain magnitude of anisotropy. How do you know whether that's from a dipping anisotropy versus just a lower amplitude of alignment or something that's actually causing the anisotropy? Do you understand what my question is?
Not really.
So if you were creating this anisotropy, let's say from LPO.
Yes.
Okay. And that gives you a certain magnitude of shear waves of variation in the speed of the SV and the SH.
Yes.
So, but how can you tell the difference between whether that is just a purely horizontal flow or dipping, but you're only measuring a small component, right, of the horizontal part?
Yeah. Okay. The extreme case is when you have a vertical flow.
And then it's zero. I understand.
From tomography, we can retrieve the different azimuthal terms. I will show some example.
Okay.
If you have no azimuthal term, you have different kinds of interpretation, but basically it can be either fine layering or it can be a vertical orientation of the crustals. When you have some azimuthal terms, it means that it cannot be you have some other effects, and probably you have some part of horizontal flow.
So I'm just trying to figure out how you interpret it in terms of it's a horizontal flow, but it's a small amount of shear that's creating the LPO, so it's not a strong LPO, versus it's actually a shear that's actually at an angle. Right?
Okay.
So how you actually interpret that in terms of flow, I think comes from how you interpret the magnitude of what you're seeing. Is that right?
Okay.
One answer to this is that based on the seismology, it's very hard. But if you're willing to make the assumption that there's a thing and tilt it, as opposed to one thing and shrink it.
Okay.
But you
Yeah.
need to make a further assumption about what it is.
What is
Perfect.
it? Okay. Thank you.
Okay, so I will show some example of what happened. So what I want to show is that we have the zero psi term with 5 parameters, and from the azimuthal terms, we need 8 additional parameters. But as I told you, it's a lot of parameters. And, I forgot to mention the second part. Of course, we have parameters, but we have also the depth sensitivity kernels of surface waves. So, as I told you, we have different kind of surface waves and different modes. We have the fundamental mode, and we have overtones. And basically, most of surface wave studies are using fundamental mode, and you can see that, for example, at a period of 50 seconds, surface waves are sensitive down to about 100 kilometers. But the interesting point is that if you can have access to overtones, you can have access to the deeper structure of the Earth. And so that's what is done more and more to try to retrieve overtones to have access to the deep structure of the Earth. That's the most important sensitivity kernels for surface waves. It is related to L, which is related to VSV. So that's the most important kernel. For example, for Rayleigh waves, we can show that the sensitivity to SH wave is very small. You see the amplitude is 0.06 and almost 0, whereas we have a factor -3. And so surface waves are not sensitivity in the same way to the different parameters. And the most important parameters for surface waves are SV velocity. And we have also some sensitivity to P wave, but it's difficult to invert all parameters. So what we do, we use some scaling relationship between VP and VS. Okay, so to summarize this part, we have 21 elastic moduli. We have zero psi term with 5 parameters, which correspond to the azimuthally average model corresponding to a transverse isotropy with vertical symmetry axis. And the best resolved parameters from surface waves are VSV and also the ratio between VSH and VSV, which is named the radial anisotropy. I have to mention that if you want to retrieve this parameter, you have to do a joint inversion of Rayleigh and Loeb wave dispersion curves. Another interesting point is that the variation of VSV is through the parameter G and psi G, which is the azimuth of corresponding to this parameter. And it was showed that we have some way to compare what is observed from body waves and surface waves through this parameter. It was shown by Stuart Crampin that for body wave we have exactly the same parameter which can be retrieved from surface waves. So it motivated many studies by Barbara and others to make a joint inversion of body wave and surface wave anisotropy through this G parameter. Okay, so maybe this will answer. It's a simple answer of your question about the use of seismic anisotropy. There is no necessarily a unique interpretation, but let me try to explain why. When we use seismic anisotropy, we have 2 different kinds of maps. We have at least 3 correctly defined tomographies of S-wave velocity, the radial anisotropy, which is the difference between SH and SV, and azimuthal anisotropy. And all of these maps are useful to understand the convective processes. For example, if you have again this simple convection pattern with the upwelling and downwelling and horizontal flow, from S-wave velocity we will see red and blue spots, and when it is red usually it means that it is hot, when it is blue it is cold. For radial anisotropy you see that the alignment, it doesn't matter if it is alignment for the same alignment for upwelling and downwelling. In both cases, we will have, you see, smaller than average radial anisotropy. So when we have a very small anisotropy, probably it's an upwelling. And from azimuthal anisotropy, we will have the orientation of the flow. Okay? So when you have upwelling, azimuthal anisotropy or downwelling, azimuthal anisotropy will be very small, and it will be the largest when you have horizontal flow. Okay? And
what do you mean by small? It's psi is VSV larger than VSH, but it can be large.
what do I mean by flow?
No, you said small anisotropy. It's not small. It's less than 1, right?
Okay. Less than 1 or less. Well, in that case, I normalize with respect to 1. No, I mean smaller than smaller than in that case it will be smaller than 0. Okay.
So because you said small.
Negative.
Which may be ambiguous. Maybe
Yeah, you're right.
no
It's
anisotropy. That's not what you mean.
no. We have, of course, anisotropy, but it is negative or it is smaller than 1. It depends how you define psi, and it can be several persons actually. Okay, I understand. Yes, small might be ambiguous. Okay, so we have these 3 maps, and we need these 3 maps to make some interpretation, because it will enable to discriminate upwellings, downwellings, and horizontal flow. I would like to make a simple comparison why we need these 3 maps. For example, if you want to image a famous geophysicist, Adam Dziewątki and Don Anderson, if you have anisotropic imaging, you can see the features of the face and blue and red spots. But if you have only isotropic imaging, you have only blue and red spots, and so it's very difficult to discriminate the two faces. And so it is the same in for seismic anisotropy. It enables to discriminate competing models and to discriminate between competing geodynamic processes. Okay, so I have some time to show you some applications of seismic anisotropy, and I will, of course, as I told you, we can map mantle convection, but at the global scale, Eric Debaille probably next week will show you some of his maps by using seismic anisotropy. I will focus only on the mapping of the L.A.B, Lithosphere-Asthenosphere boundary, and how we can have access to interesting information about the lithospheric routes. Okay, so the L.A.B has been defined by very different fields of geophysics. It can be defined from mechanical properties, the difference between you have the mechanical boundary layer and you have a change in the strain rates. You can use also the thermal L.A.B by considering the temperature. In the upper part, you have a conductive lead, and below, you are more related to convection. Some people also define the electromagnetic L.A.B by considering the change in the resistivity or conductivity between the resistive lithosphere and more conductive asthenosphere. And of course, what I would like to focus on is the seismological L.A.B, which can be addressed either by considering VS velocity, S-wave velocity, where we have a high velocity lead and we have below low velocity zone with a decrease in velocities. And we will also look at the seismic anisotropy, where we can expect some change at the level of the L.A.B between the upper part and the lower part. Okay, so it's a old slide, but 5 or 6 years ago, people realized that there was a discrepancy between different kinds of measurements of the L.A.B. When you use receiver functions, you see, for example, from Reichert and Shearer that you have, of course, only in continents, L.A.Bs up to between 60 and 100 kilometers. And from surface waves, usually we find that the continental routes are down to about 200, 250 kilometers. And in order to reconcile this observation, it was proposed to introduce mid-lithospheric discontinuity, and so probably what is measured here is a converted wave by this mid-lithospheric discontinuity, and there is some way to reconcile these two estimates of L.A.B. Okay, so I will show you what we can do from surface waves what we did from surface wave dispersion. We applied two different techniques for solving the inverse problem. We use a statistical Monte Carlo approach. In that case, we have 4 layers, and we investigate different parameters, variation in velocity and variation in the depth of the L.A.B. And here we have the asthenosphere, and we also explore the parameter space in velocity and the thickness of the L.A.B. and so on. What is another classical technique is the first order perturbation theory, where you have VSV as a function of depth, which is obtained by inversion. And when we calculate the gradient, we find that there is a maximum of the gradient for some depth, and we will say that it is a proxy for the L.A.B. Let me detail this point. Of course, seismic waves have very long wavelengths, and so they cannot easily detect sharp discontinuities. And what we see actually is a filtered version of this parameter P as a function of depth. But we can show that if we calculate the gradient as a function of the radius, it will have a maximum, and we at the same location as the discontinuity. So it's not a very accurate measurement of the location of the discontinuity, but we can expect that we will have a good lateral variation of this discontinuity by using this technique. Okay, so that's a complex figure to show that we can use different anisotropic and parameters. As I said previously, we have some well-resolved parameter, which has VSV, S-wave velocity, Xi, the radial anisotropy, and the two parameters related to S-wave azimuthal anisotropy. So if you consider VSV, you see by using the gradient technique, we have access to proxy of the L.A.B. And again, by using radial anisotropy, we'll use the fact that the gradient is in opposite but also has a maximum. We also investigate the influence of the variation of the azimuthal anisotropy through the amplitude and the azimuth. And so that's an example in an oceanic profile. And I will basically focus on oceans. For continent profile, it's much more difficult because you have not so well-defined low velocity zone, and sometimes it's not so easy to define the L.A.B. in continents. So I will only show some results for oceans. Okay, so we did a compilation of many. As I told you, we have so many data that we can have hundreds of thousands of measurements of Rayleigh and love waves, fundamental and higher modes. I will not detail. And that is the maps we can obtain at different periods. So that is the first step, what I named the regionalization at different periods, at 50 seconds, which is a wavelength of about 200 kilometers, and that longer period, 100 seconds, which means a wavelength of about 400, 500 kilometers. And you see that what we plot here is, for example, is a fast velocity in blue and slow velocities in yellow and red. And you see we have an amplitude of about plus minus 5%. It's not a lot, so it justifies the fact that we can use first order perturbation theory. And we also plot here the orientation of the azimuthal anisotropy at the surface of the Earth. And when we have the different maps, we can do the inversion at depth, and we use the two different techniques I mentioned. We did a statistical Monte Carlo inversion, and we did a first order perturbation theory. And I will show the results for both of them. Okay. For the statistical Monte Carlo inversion, we only consider the isotropic variation. And we explore the L.A.B. So what I show here is the depth of the L.A.B, Z-L.A.B here, And we find, of course, mid-ocean ridges very well. And we also find the roots of cratons here, so nothing really new, but we find very nicely. And we also find the variation of velocity between lithosphere and asthenosphere. So that is the kind of map we can retrieve.
I have a question. So you mentioned before that you cannot explain low and Rayleigh waves if you don't introduce an isotropy. But here you do.
In continents. Yeah, no, okay. I mentioned that on continents it's much more difficult to use a radial anisotropy signal because it's not so well defined. And I showed only the inversion from VSV here, okay? I don't use the information from...
Because the data you show low and Rayleigh, so it's confusing. I'm confused.
Yeah, we are using old data, and it is the best. You can use Rayleigh and love waves even for an isotropic search, no? So it is what we did. We only, in that case, we search what is the best model explaining at the same time phase and group velocity of Rayleigh and love waves.
And we can get one isotropic model.
Yeah, but not perfect for love waves. Actually, we put more weight on Rayleigh waves in this statistical inversion. Yeah. But it is the best isotropic model we can get from this data set. But we don't explain many love wave dispersions, of course.
So here you have both a blue and a purple line on velocities, right? So what's going on? I mean, what's the purple line about? Seems to be underneath the blue line.
You are right. What is this? It is I guess the students start different starting models probably, but I don't remember the detail. What is important is the blue line. I should have removed the purple lines.
The purple, it looks like you don't have a jump at the L.A.B level, right?
No. But I guess forget this purple. It's not important. What is important is the blue line. Okay. That is really what we do to explore the depths. Yeah.
I think in the previous slide you showed purple was the
Sorry?
I think in the previous slide you showed that purple was the prior.
No. But previous slide. This one? No.
That. Oh, the blue was the prior. Oh, it's different. Sorry.
No. They are not related. Okay. So that's the first estimate of the lab by isotropic inversion. And now I will show you the other estimate by using first order perturbation theory by inverting at depths VSV, azimuthal anisotropy, and radial anisotropy. And so that's the maps at different depths. I don't want again to detail. It was some other models found very similar maps, but I only want to show the information we get for the lab. Okay, so again we are using this proxy of the gradient here, the maximum gradient, and that is what we get. And we get again mid-ocean ridges, but we find thickness of cratons which are thicker than from the isotropic inversion. But it's quite a classical result. We see all cratons and all subduction zone and all mid-ocean ridges. What is much more interesting actually and very surprising was when we apply the same technique to the radial anisotropy derived from Rayleigh and low wave inversion. And we are very surprised. In that case, we take the minimum of the gradient. Well, it is a function of depth, so it is a minimum. And what we only apply this technique to oceans, because as I told you, in continent it's much more difficult. And what we observe is that we can see some mid-ocean ridges, but we see that it's very uniform. And that was a real surprise because we were expecting to see something very similar to what we got from VSS wave. And if we have the three maps, we find three different maps, and not really, and in a sense, quite different. Okay, if we compare the first one, statistical inversion, or the first order perturbation theory inversion, in the anisotropic scheme, we see that the influence of anisotropy is important because it tends to change the depth of the root of continents. For example, for the anisotropic inversion, we find usually for most of cratons deeper L.A.B than for the isotropic inversion. So it means that the influence of anisotropy is important for getting a good estimate of the L.A.B. And for the radial anisotropy, we find a completely different image. We find that it is almost uniform in all oceans. And this result was not really expected when we started this investigation.
Jean-Paul?
Yes?
Could you explain exactly what you mean by why is the Xi a proxy for the L.A.B? You're just saying you're going with one kind of anisotropy,
Oh.
none, or change in anisotropy?
No, what we, for Xi, we have this kind of profile with depth, and so we can also we make the hypothesis that this increase is due to some discontinuities somewhere. Okay, and we assume that the maximum is in the low velocity in the asthenosphere, and so we only look at what is the depth of this maximum of the gradient. So we calculate maximum in the minimum actually in that case. Okay, so it is also to find some discontinuity somewhere in the upper mantle. Okay, so the same approach as for VSV, but applied to the radial anisotropy.
Okay, but not directly related to temperature, for example.
No. There is no hypothesis. It's only measurements, and we derive the map of this gradient here. And what we believe is that if we plot for the Pacific Ocean here, we have all measurements. So we put all the points, and we compared with the half-space cooling model. I guess it was mentioned 2 days ago that when you have the half-space cooling model, you know that it doesn't work very well except maybe for the anisotropy derived from azimuthal anisotropy. I didn't detail how we get that, but it was the same approach, and we see that for azimuthal anisotropy we have this half-space cooling model, which is not too bad, and it works for VSV up to about 70 million years, but it failed in both cases for age older than 70 or 80 million years. From Monte Carlo inversion, of course, it's even in a complete disagreement, because you see that even at 50 million years, you start to be away from the half-space cooling model. And of course, what we find for the radial anisotropy is that we have almost a constant depth for this discontinuity, and which is completely different from the other observation from S-wave velocity. And what we observe for the Pacific Ocean is also clear for other oceans, but I show you another plate model. It's taken from a paper by Dan Mackenzie, and even with this plate model, it's not so good, except maybe for the radial anisotropy, where we have almost constant depth, but it doesn't work very well for the S-wave velocity or azimuthal anisotropy. Okay, so far the oceanic plate model are not so good. And what we find for the Pacific Ocean is also found for Atlantic and Indian Ocean, where you see that we have not so bad for the Atlantic Ocean compared to the plate model for here VSV and Indian Ocean. But of course, what we find is again this kind of discontinuity, proxy of discontinuity obtained from the radial anisotropy. So something is happening around these depths between around 60 and 70 kilometers. And of course, we can find that because we took account of seismic anisotropy. And so we propose a very simple model, but I'm not sure it is real. It means that we have the oceanic plate is not so simple. We have, of course, some partial melting close to the ridges, and we have some dehydration, and probably we have incoherent large-scale anisotropy and small radial anisotropy. And what we show here is a thermal lab, which corresponds to maybe the plate model or any other model. And so we have the difference between the upper part of the lithosphere and the lower part of the lithosphere. And in the lower part of the lithosphere, we have an increase in the radial anisotropy. And so now the structure of the oceanic plate is much more complex than what we were expecting before. And of course, it has to be taken into account when we define plate models. Okay, so I still have, I will try to go faster.
I have a question.
Yes?
Do we have a microphone, or did we just give up on that? Okay. Can you comment on how these results compare to the work of Begin and Schmer and whoever that was published in Science recently, where they were also looking, if I remember, at the variations of velocity, azimuthal anisotropy, and radial anisotropy underneath
actually,
the ocean?
it is following about the same ideas. In a paper by Caroline Begin, they looked at azimuthal anisotropy and also found some discontinuity in the oceanic lithosphere. So we have to make more quantitative comparison, but it is on the same line, yes. This kind of mid-lithospheric discontinuity within the oceanic lithosphere. Yes?
Now that Ved brought up Schmer's underside reflections, we had a paper, I guess last year in GIL, where we, followed up on the Burgos et al. Study that Jean-Paul just presented and Caroline's work, and we looked specifically at this issue if the radial anisotropy within the oceanic lithosphere has a half-space cooling sort of dependency or if it's flat. And I, based on the data set we used, it's sort of hard to tell, but I think we sort of, for the most part, we confirmed what Jean-Paul has just described, very much so. But my comment here is that turns out that Nick didn't just have these underside reflections at a large depth. There are also these shallower reflections that are pretty much flat as well. And it seems like that those two layers in the reflections border this region of high radial anisotropy. And the azimuthal anisotropy, as was pointed out by Jean-Paul and Caroline, does seem to follow a half-space cooling profile, which would be consistent with half-space cooling controlling the mechanical strength of the boundary layer, but then having some sort of frozen-in structure within the lithosphere, as Jean-Paul just said.
Inherited boundary due to the creation of plate at the mid-ocean ridges, probably.
We have an author on that paper here, Cijk.
Oh, yes. Okay, so what we show is that by using seismic anisotropy, we can find some new discontinuity, and actually it's very similar to what was done for continents by Yuan and Romanovich. And so, of course, we have to make more work to understand better this kind of discontinuity and what are the petrological and geodynamic implications. Okay, for continents, maybe I will not have I would like to finish. Okay, my student, unfortunately, is not here today, Satish Maurya. He did recently a study of the Indian continent. And Indian continent is interesting because so far it was a seismological desert because it was impossible to access data, seismic data. But it's a very interesting continent because it is not too large, and you have many cratons. You see here in purple. We have also the Deccan volcanic traps, and we have the Himalaya chain. And so it was interesting to look at this continent to understand also why he moved so fast 50 million years ago. And I will not detail all what we did, but we had access to the seismic data from the Indian networks, and they have a lot of data accessible, and I will only show results. Okay, so what we did, we use about 500 stations, and we derived at the same time velocity and azimuthal S-wave velocity and azimuthal anisotropy at different depths. And the interesting point we will see later is that we see a large variability in the thickness of continents. And what we see is some kind of, in the middle of the continent, we have some kind of high velocity body, which is visible down to 200 kilometers, but not other cratons. And we wonder what is the origin of this keel, by the way. And I show some different cross-sections. And okay, so we have here the different profiles, and we see the blue velocity and the map of the lab, and we see a large variability between. You have a lot of different cratons, small scale, but at 500 kilometers, and we see that we have a large variability of the thickness of these cratons, and we see this low velocity zone here around 80 kilometers, which was also found apparently in North America, but it's visible in almost all profiles, but not all of them. For example, it's not visible here, it's not visible here. So it means that what we call a continent or even a craton can have a very large variability. And I only show 2 examples. And on this cross-section, we have this low velocity zone around 80 kilometers, and we see this keel here, which is a K3, K4, which is a here east-west profile, and we see this very fast velocity body. And it's not always the case. We don't understand some of the features, but we see that all cratons do not have the same thickness. For example, this one, EDC, I forgot which one is it. EDC has only a route down to about 120 kilometers, but in the central India here, CI, we have a depth up to 200 kilometers. And we can make some comparison also with azimuthal anisotropy, but the main feature is this keel, and we don't understand, this keel, what is this geodynamic interpretation. And we also looked at azimuthal anisotropy, and again, we look at the angle, and we found that we have no systematically the mid-lithospheric discontinuity. We tried to make the comparison of this gradient of azimuthal anisotropy, but it's not present everywhere. For example, here we have no for some West Darwar craton, which is here. We have no this kind of mid-lithospheric boundary, which is actually a low velocity zone. So this kind of small continent with different pieces of blocks show a large variability, and I suspect that it is the same in North America, and that when we discuss cratons, we are discussing of different kinds of objects. And of course, I told you what was the surprise was this keel here, and we can wonder this keel, which is this kind of object you see about 1,000 kilometers long and quite narrow. What is its geodynamic role? Because you know that India moved very fast in the past at 20 centimeters per year when it came from the southern Indian Ocean up to the north. And is this keel the result of the erosion? How does it affect the northward motion? Is it like a keel of a boat which drives you away? We don't really know. I have still Okay, so the study of this continent is interesting because it shows that we have a large variability of the craton thicknesses. We have, or we have not, a low velocity zone in some cratons, and we have, of course, this Indian keel. So let me finish by an issue which was addressed yesterday about attenuation. Okay, I have still 5 minutes. Okay, so we discussed on the fact that attenuation, the quality factor, is almost constant in the large frequency range between 10,000 seconds to about 10 Hertz, and a constant Q. And of course, Uli proposed a different interpretation, but the classical interpretation was in terms of absorption bands, and even though Vett found some small variation of Q with frequency, basically it is close to 0. So if we consider that it is close to no frequency dependence, we can consider this kind of standard linear solid and with attenuation peak. And to explain this constancy, we need a lot of absorption band, which is a way to reconstruct this constancy of Q. So with Yannick Ricard, we said, okay, maybe this interpretation is quite artificial. We could try to find something else. And we looked at the scattering. As I told you, when you have anisotropic material, if you have some random orientation, you will tend to create some scattering. And this scattering will have an effect if you have a pulse, initial pulse like that. If you have scattering in the medium, you will tend to have some delay, and you will tend to change the amplitude of the initial pulse. So it is not intrinsic attenuation, it is more an extrinsic attenuation, and we can try to model this kind of apparent attenuation. I did what we did with considering a 1D simple model. So we consider a random distribution of heterogeneities. It can be either heterogeneities in density or heterogeneities in seismic anisotropy. And so we have this kind of very complex heterogeneous 1D model. And we can calculate the power spectrum of this kind of model. And we realize that, okay, I am not working in fluid mechanics, but apparently there is a case which is named the Bachelor regime, where you have the power spectrum varying in 1 over k, where k is the inverse of the wavelengths, of the spatial wavelengths. And this kind of k-1 Bachelor regime seems to be one possible regime in the mantle convection. And in that case, you can make some numerical modeling, and you can investigate the mixing when you have this kind of Bachelor regime. And what we found is that when we calculate the equivalent quality factor for different wavelengths, we were able to reproduce a constant Q by using this kind of Bachelor regime with this kind of specific power spectrum. Of course, it is we replace the complexity of the absorption band by the complexity of the distribution of heterogeneities. But this kind of Bachelor regime is quite simple because it is only dependent on one number. So we don't say there is no intrinsic attenuation in the Earth. What we believe is that the scattering due to this kind of heterogeneities, complex heterogeneity, might give rise to this kind of constant Q, and it might be also a side effect of the presence of anisotropy within the Earth. And for getting this constant Q, we don't need so so much amplitude. Only between 6 and 9% amplitude of anisotropy or density variation is sufficient to reproduce this constant Q. So I guess it's interesting to mention that I didn't know the results by Uli, who mentioned that he has another interpretation. I don't know which one is correct, but that's a possible explanation. Okay, so to conclude, what I tried to show you is that seismic anisotropy is necessary to explain seismic data, and it can be mapped in a different depth range. And we still have many challenges because the interpretation of seismic anisotropy is non-unique. It's, of course, we have intrinsic LPO, which give information about the flow in the mantle, but we also have some extrinsic anisotropy, which must be taken into account. Seismic anisotropy enables to map some geological objects, such as L.A.B, and by using seismic anisotropy, we can make some new finding. And of course, it's only the start of what we have to do. What we have to do now is to develop new tools, new numerical techniques and approaches. And I guess Thorsten will present some numerical techniques to calculate the flow inside the mantle. And a difficult issue is the separation of the different causes of anisotropy and to separate extrinsic and intrinsic anisotropy. Okay, thank you for your attention. Yes?
Where's the mic?
Just to comment, as we discussed, right, so from spectral element modeling, and the seismologist can comment on that better than I can. Colleen found that at shorter frequency, higher frequencies, there is some contribution, but it's very small. But at longer periods, as you discussed for surface waves, there's essentially no contribution from scattering. Mentioned just the spectral element modeling of seismograms. And the other two parts was that, in terms of generating heterogeneity or anisotropy, the models that you had at the beginning, right, cracks are a brittle phenomenon, and you have that in the very shallow crust. In the deeper crust, even pressure will close cracks. So cracks as such won't contribute to heterogeneity or anisotropy. That's something for exploration seismology, for example, where it's important, but not at surface waves. And the milfoil model, that is also, of course, controversial, right? You have to look at what the alignment is. Well, first off, you have to have a stress-controlled melt distribution, not a surface energy-controlled melt distribution. Mm-hmm. That's one assumption.
So
the second
we go back to the first point about. Yeah, I agree that the scattering is not present everywhere, and I agree with you that at short period you have a lot of scattering, and you do not have so much scattering at very long period. Yes, I agree with you. It's clear, but so it doesn't mean that it is the end of the story, because if you have some this kind of mixing, maybe it cannot be retrieved by the effect at long period is not necessarily so simple. I don't know. So I'm not sure that this kind of mixing, when we have some kind of marble cake model, it might also have some long period signature. I don't know how. It has to be investigated, but.
Okay, I just wanted to comment on the melt distribution.
Yeah. I have to read more carefully at this paper. It was published. You just sent me yesterday. Okay. I will get
the melt distribution of the Lithosphere-Asthenosphere boundary, even if it's stress controlled, right? The anisotropy that you get out of that isn't entirely straightforward, because you then have to look carefully at the experiments, which seem to suggest that in some cases at least the melt has an angle with respect to the shear plane, right, which then wouldn't give you exactly that flow parallel alignment of the melt pockets. And even then, the anisotropy that you calculate for the aligned melt bands isn't entirely straightforward, isn't directly comparable to what you would expect for the simple olivine P-wave velocity and anisotropy. So there are complexities in detail in any of these mechanical models that are invoked to explain the anisotropy. Alignment, like large volume alignment of olivine, is still the simplest explanation for anisotropy.
Yeah, no, I agree. But, okay, if I consider the case of the low velocity zone, it's interesting because you have the millefeuille model where you have pockets of melts, but by this kind of model, you cannot explain everything. For example, you cannot explain azimuthal anisotropy in the low velocity zone. So it means that even though you can have some fluid inclusion, some melt pockets in the low velocity zone, you have probably in addition some intrinsic anisotropy, which is measured through azimuthal anisotropy or through shear wave splitting. So we have both effects, and the relative amplitude of this effect is not easy to find.
So I have actually first a comment and then a question. The comment first is that when you talk about the SPO, the shape preferred orientation, you said it was mostly stress control. I can agree with that in some environment, but there's also, especially in the lithosphere, there will be effects of strain also that produce shape preferred orientation because
of course,
material gets sprayed.
Both are related because we have a relation between stress and strain. Yeah,
right, so I just wanted to mention that because it's not just stress.
No, of course, because stress and strain are related through the elastic and the viscous tensor.
Yeah, but especially in terms of frozen anisotropy, right? The directions you would get from an old anisotropy may not be the same as what you would infer today from convective patterns, of course. Just trivial things that have to be mentioned. The question I have is going back to the Monte Carlo inversions that you did of the anisotropy there. So you have different depths of which the transition from two layers happen. But if you go close to the ridge axis, that's about the same depth as what you have with the other methods. And so I'm wondering if the amplitude of the jumps that you get at the L.A.B. Also has some kind of dependence on location.
Yeah.
Not just its depth, but its jump.
Oh, wow. I'm going too fast. Okay.
Because, I mean, if there's two different origins
this one
that are superposed,
Mm-hmm. Yeah, so we so far we only looked at the map of the lithosphere, but of course we also have some information about S-wave velocity, and we.
But I don't mean necessarily the S-wave velocity, but the jump across it.
Mm-hmm. That is a jump actually.
Oh, that's just a jump.
Oh no, it is absolute value. No, it's not. I have another map with a jump, but not here. No, we also have the jump, but not very well constrained actually. But
and no pattern. Geological interpretation you can make on that?
No, we have no. Okay. Yeah, we have to look more carefully probably at this velocity jump. But
one important announcement before our coffee break, and unfortunately it's a long announcement. If you looked at your agenda, you probably noticed that this afternoon at 4:30 there's something that hasn't been on the agenda yet. It says first discussion of group research projects. So let me remind you where Barbara started on Monday. She said that we're all, of course, here because we're interested in the structure and evolution of the Earth. We're seismologists and geodynamicists, mineral physicists, and geochemists. We're using different tools to answer similar questions that are connected to flow in the deep Earth. And so what we're going to do at 4:30 is have our first discussion of topics that would make suitable projects for group activities over the upcoming few weeks. This is our first of these discussions. And so at 4:30, those of us who don't fall in the category of senior participants will be quiet, and everyone else, and that means everyone, will be suggesting questions that would be good topics for these activities. And so this means both the questions, and as you think about questions, think about whether, what it is that you can actually accomplish over the next few weeks, and what might have to continue beyond this, and whether these projects and questions are integrative and would involve multiple disciplines, and who here brings together the right expertise. There won't be 42 questions. That's way too many. And so, of course, someone may suggest a question that's very similar to the one you would like to work on or discuss. And so then you should feel free to add to or complement what other people say. Ved's going to moderate that discussion. And last point, this discussion will not be recorded, right? So it won't be broadcast to the world. But I will be writing everything on the blackboard, of course, so we internally have a record of that discussion. Let's thank Jean-Paul Montagner.